Greetings everyone, I'm Ashi. Today together with my friends Amaline, Amy and Nicholas, we will explore one of the cornerstones of physical science, the second law of thermodynamics.
This law covers the directionality of the energy transformations. It's essential in explaining how heat engine works, how refrigerator function, and even why time seems to move forward.
We will start by reviewing the first law, energy conservation, and then explain why it isn't enough on its own and needs second law to fill the gap.
With the help of animation, real-world examples and exercises, we will make this concept not just understandable but meaningful.
In previous chapter, we learned the first law of thermodynamics. Energy cannot be created or destroyed. It can only transform. For example, when coffee cools, heat energy leaves the coffee and warms the surrounding air.
Now, consider the reverse conditions. Coffee heating itself by drawing heat from the cooler room air. That never happens. Yet, it wouldn't technically violate energy conservation.
Similarly, a resistor converts electrical energy into heat, but we cannot reverse the process and generate electricity from ambient heat without special devices. In the pedal wheel setup, heat from water is imagined to drive a wheel and leave a mess, while energy balances such as process that doesn't spontaneously occur.
So why the first law tells us how much energy is involved, it doesn't indicate whether a process is physically possible. For that, we need the second law.
The first law about energy quantity, but the second law introduces energy quality. It defines the feasibility and direction of processes. For example, a hot drink cools naturally. The reverse, gaining heat from cooler surrounding, never occurs spontaneously.
Kelvin Planck's statement, no heat engine operating in a cycle can convert all the heat from a single reservoir into work without some heat being rejected to a colder sink.
That's why 100% efficient heat engines are physically impossible.
Clausen's statement, heat cannot flow spontaneously from the cooler body to the hotter body without external work.
This is why refrigerator needs power that moves the heat against its natural direction from cold to hot by doing work.
A thermal reservoir is something so big that its temperature doesn't change when it gives or receives heat. We often use two types, a hot reservoir like boiling water and a cold reservoir like ice or room air.
A heat engine takes heat from the hot reservoir, does some work, and releases leftover heat to the cold reservoir. These reservoirs help us study heat flow and understand real systems like power plants and also refrigerators.
Entropy is a thermodynamic property that measures the level of disorder or how dispersed energy is within a system. For example, when a gas expands into a vacuum, its molecules spread out randomly. The system becomes more disordered, its entropy increases. The reverse never happens on its own.
Entropy form of the second law. In an isolated system, the total entropy never decreases. It either remains constant in an ideal cases or increases in real processes.
This is why natural processes are irreversible. Ice melts, gases mix, and batteries discharge, all leading to higher entropy.
Though the total energy remains constant, it becomes more even spread, less concentrated, and thus less capable of doing useful work. Entropy introduces a thermodynamic error of time. It explains why we observe the past but not the future, because entropy increases with time.
A reversible process is an idealized one that can proceed in both directions without leaving any net change in the system or surrounding. These processes are purely theoretical but serve as a benchmark. They represent the maximum efficiency achievable under perfect conditions.
To be reversible, a process might occur infinitely slowly, involve no friction, turbulence, or large temperature difference. For example, compressing a gas process statically in a perfect insulated prisonless cylinder is not real but useful for analysis.
In contrast, irreversible processes dominate a real world. Frictional motion, suddenly expansion or compression, mixings of fluids, combustion reaction, and also heat transfer with large temperature differences.
These all generate entropy, and once they occur, the system cannot spontaneously return to its initial state. Understanding these differences helps engineers optimize systems. balancing ideal models with real-world constraints. A process is internally reversible if no irreversibilities exist within the system itself.
It's externally reversible if interactions with the surrounding are ideal, like heat transfer, across an infinitesimal temperature difference.
A totally reversible process has both no internal and also no external source of irreversible.
These processes are hypothetical, but they help define the upper limit of system performance and serve as a model in thermodynamic cycles.
Let's apply what we have learned with a few short exercises.
Exercise 1. A block slides down an inclined plane with friction and no restraining force. Is this process a reversible or irreversible? Justify your answer.
So the answer for exercise 1, the process is irreversible. This is because friction is present, which causes the energy to be lost as heat. Once the block has slid down, it won't return to its original position on its own. To reverse the motion, external work must be done. Since entropy increases due to a frictional heat, the process cannot be reversed without leaving a change in its surrounding.
A cold canned drink is left in a warmer room where its temperature rises as a result of heater transfer. Is this a reversible process? Explain.
No, this is not a reversible process. When a cold drink is left in a warm room, heat flows from the warm air to the cold drink, making it warmer. This heat transfer happens naturally and cannot be reversed on its own. To cool the drink back, you would need to use something like a fridge, which requires extra work. Because the process cannot go backward without help and increased disorder, entropy, it is irreversible.
To summarize, the first law addresses the conservation of energy, but the second law explains the direction of nature processes.
In practical systems, energy degrades. High-grade energy, like mechanical work or high-temperature heat, become low-grade and less useful.
Reversible processes define theoretical performance limits. Real systems are always irreversible and subject to the entropy increase.
Thank you for watching. Keep exploring the wonders of thermodynamics. Don't forget to like, subscribe, and review the exercises in the reference book.